Hello, I'm going to do a really short problem today on why you should wear your seat belt. So forces in physics will give us the answer. We are going to suppose that you're going 40 miles an hour in your car when your car gets a flat tire and you veer straight into a tree, coming to a stop. If you're wearing your seat belt, you stop moving over a distance of approximately 1 meter. What is the approximate force the seat belt exerts on you to stop you? And let's assume a mass of 65 kilograms. This is just, standard person, standard car. We're going 40 miles an hour. Let us get started. First thing, draw a picture. Okay, so you're in the seat. Okay. And you've got the steering wheel. There's my picture. Picture, knowns. We're assuming a mass of 65 kilograms. It's kind of a small mass. We're going 40 miles an hour, so our initial velocity, miles an hour, got to convert it. If we convert that, it's 18 meters per second. And the distance over which we come to a stop is about 1 meter. We want to know what is the force of the seatbelt. Picture knowns, unknowns. Next up, we want to do a force diagram. So what object are we going to pick? Well, we have the mass of the person. We want the force on the person. Let's do the person. Seat is exerting a normal force, and the earth is exerting a weight downward. If we're moving this way and coming to a stop, our acceleration should be that way. So I'm going to guess we have an unbalanced force that way, and that matches with the physical situation. The seat belt is exerting force this way on us. I'm not going to worry about the friction on the seat. This is just a real quick estimation of the types of forces. All right, so we've got our force diagram. I'm going to say the acceleration is this way. We want to pick a coordinate system that matches our acceleration. And XY chart. Oh, let's figure out balanced and unbalanced. In the X direction, unbalanced, clearly, there's only one force. Y direction, I have two forces. There's no motion up, down, hopefully. I'm going to say in the Y direction, it's balanced. X direction forces. We have a negative force of the seat belt, and that's got nothing in the Y direction. We've got a positive normal, and we have a negative weight. All right. We now do our sum of the forces in the X and the Y direction. So I said this was unbalanced. So the net force in the X direction equals MA in the X direction. Add up all the forces in the X direction. There's one of them. That's easy. Negative force of the seatbelt equals mass times acceleration in the X direction. Y direction, I said it was balanced. There's no acceleration. So the net force in the Y direction equals mass acceleration Y. That's 0. So this is going to add up to 0. Positive normal. Negative weight equals 0. There's my two equations, and this is again the key to solving these force problems is getting to this point. And we want to know what the force of the seatbelt is. Here's my equation. I know what my mass is. I need to know what my acceleration is. I have enough information to solve this with kinematics. So I'm going to go back and do this with the kinematics. X initial, X final, V initial, V final, A, T. I need to know what my acceleration is. I'm starting at 40 miles an hour, which is 18 meters a second. I come to a stop, and I come to a stop over about 1 meter. I don't have time, so I'm going to use this one and hope this works for me. 0, V final is 0. So 0 equals V initial squared plus 2A delta X. If I solve that for acceleration, I get a negative V initial squared over 2 delta X. 18 squared over 2 times 1 meter. Final minus initial is a positive 1 meter. My acceleration in this case is about 160 meters per second squared. That is 16 times gravity's acceleration, so that's 16 G's. That's pretty big. Go back, put it in here, and I'm out of space. So I can ignore this. I'll just erase this. Figure out what my force of the seatbelt on me is. Force of the seatbelt, so negative FSB equals the mass, which was 65, times acceleration, negative 162. Running out of space. If I do the math there, it's about 10,000 newtons. Around 10,000 newtons, which is around 2,400 pounds. All right, so that's if you wear a seatbelt. That's the force the seatbelt is exerting on you, which is significant. I mean, that is a large force. This is why if you've ever been in a car accident or know someone, the seatbelt often leaves a pretty good bruise. Let's figure out what would happen if you weren't wearing your seatbelt. Suppose your passenger was not wearing their seatbelt, and they're thrown forward into the windshield. Now, the windshield makes them stop over a distance of about 1 centimeter. What force does the windshield exert on them? Same picture, except that now the force of the seatbelt is the force of the windshield, and we're going to change this to 1 centimeter, which is 0.01 meter. This is all true, this is all true, this is all true, except now it's 0.01 meter. So I don't have to go through all the physics again. I can just replace the delta x with 0.01, and that will give me, let me find a good place. When I do that, the acceleration from the windshield stopping you is 100 times bigger, which is now 1,600 G's of acceleration. And the force then from the windshield, if we assume the same mass, that's going to be, how many zeros here? That's a lot of zeros, which is around 240,000 pounds. So if the seatbelt brings you to a stop over 1 meter, then your acceleration is smaller, the force exerted on you is smaller. The windshield brings you a stop over 1 centimeter, that's squishing your head pretty much. The windshield's stopping you with an acceleration that's 100 times bigger, which means the force on you is 100 times bigger. Seatbelt, about 2,400 pounds. The windshield, the force of you on the windshield, or the windshield on you, excuse me, 240,000 pounds. And this is why we have seatbelts, is they stop you over a bigger distance, which reduces the acceleration, which reduces the force on you. So, please wear your seatbelts. They're really important.